Today we study Gauss Law. Gauss Law is a very useful tool to compute the electric field in case the charge distribution has a certain symmetry. First, we study the electric flux. Electric field flux is a very useful concept to compute the electric field by making use of Gauss law. If a uniform electric field that penetrates a flat surface of area A perpendicularly. This is a flat surface of area A. And electric field penetrates this surface perpendicularly, the E. In that case, electric flux phi. The lower case of phi is this one, and the capital letter for phi is like that. So electric flux is the electric field E times area of the surface that is perpendicular to the electric field. The differential area vector dA is a vector defined by the magnitude is the area itself, and there is a unit vector n hat that is a unit normal vector. And for example, we have a sphere, and sphere has a surface that is curved. In that case, to make it flat, we divide into a small piece, and this tiny piece of area has area dA, and the direction of the surface is normal to this tiny plane. And this tiny plane is called the differential area vector. So n hat is the unit vector that is normal to this tiny area, and dA is the area of this tiny area. We call dA vector that is a differential area vector dA. In general, the electric field flux d phi through a differential patch element. This differential patch element is the same as differential area vector element. With the area vector, dA is defined by the scalar product of E electric field and dA. Now, if the surface is flat and the surface is normal to the electric field, it used to be E times A, but in case the surface is curved, then E scalar product with the dA vector. And this scalar product is the product of the magnitude of the electric field and area of the patch element multiplied by cosine theta. So the cosine theta here is between +1 and -1. And if it is a plus 1, that is electric field, E field, and dA, they are parallel. If it is negative, minus 1, then the electric field and area vector dA, E, they are opposite. If it is possible if the cosine theta equals 0 when the electric field and differential vector, area vector, they make a right angle, then cosine theta equals 0. So flux is proportional to the electric field and area, but there is an additional vector cosine theta determined by the directions of the surface area and the electric field. Total electric flux is the flux integrated over some surface. So integral of the phi integrated over the net surface, total surface. For example, if it is a sphere dA, the sphere surface S, then dA vector times electric field integrated over this spherical surface. Okay, that is phi. That is integration of d phi over the surface S. Alright. Next, the net flux penetrating a closed surface is given by, we have integral over surface. For example, surface is a kind of form and surface is a sphere. It's a closed surface. It is open surface. So if we carry out the integration, if the surface is closed, we put a circle on integral sign. So this one means S is closed. S is closed. This is sign, this circular sign, the integral represents that S is closed surface. Okay, the symbol. This symbol indicates that integration is over the closed surface. The direction of dA is determined by the normal vector n, unit normal vector n. Is going out of the volume. We have some volume, and this volume is enclosed by a closed. V is enclosed by a closed surface S. That is enclosed by the closed surface S. Okay. S, V is a volume. This partial, this sign is represents the boundary of V. If the surface is the boundary of a volume, then we say this surface S is a closed surface. This represents the boundary of the surface of the volume V. Number 2, Consider the electric field due to a point charge Q at the origin. Point charge Q is placed at the origin. We introduce a closed surface as made of a sphere of radius r. Sphere of radius r. Centered at the origin. Centered at the origin. Q is placed centered at the origin. Original. A point on a sphere with the position vector r. A point on a sphere here. And this is a position vector. Position vector r is conveniently represented by the spherical polar coordinates. We use spherical polar coordinates. The radius r is the distance from the origin. Radius r. It is apparent the radius r is this. Polar angle theta. Polar angle theta in three-dimensional case, the angle is measured from the z-axis, and we have z direction, that is k hat. We have a radial direction, and the two vectors make a plane, and this is the angle. Polar angle theta is the angle between the radial vector r. Polar angle theta is the radial vector, angle between the radial vector r and the z-axis. And azimuthal angle is another angle. This plane is actually, this is a theta, and this one is a plane. This is a kind of plane. And this plane and the xy plane, they cross. Okay. Then from the x-axis, rotate about the z-axis by phi, angle of phi. This is called azimuthal angle. Azimuthal angle. And we have radius r, and we have another coordinate, another vector, planar. The radial vector has the xy component. Radial vector has xy component. Can find the foot. This vector is called rho. Xy component of the radial vector is called rho vector. So simply the radius r, using Pythagoras theorem, coordinate x, y, z, and origin, the straight line connecting the origin and x, y, z. This point, the field point, is just the square root of x squared, y squared, z squared. Right? So this is x-axis, y-axis and z-axis, then this is g, and this length is the square root x plus y, x squared plus y squared. Therefore, this length is the square root of x squared plus y squared plus z squared. And this one, square root x squared plus y squared, that is the length of rho. This amount, this one is the length of rho. That is the magnitude of a rho vector. Rho. Okay. So rho vector, we have magnitude, this one, and rho can be computed. This is r, this is theta, this z-axis, theta. So this length is rho. R sine theta. Sure, this distance is z. That is r cosine theta. Because this angle is a phi, rho has two components. Rho vector is x component, it's y component. And x component is rho cosine phi. Y component is rho sine phi. As is shown here, z equals r cosine theta. Because x squared plus y squared plus z squared equals r squared, rho squared equals x squared plus y squared should be the same as r squared minus z squared. That's the reason why it was written in this form. Therefore, x equals rho cosine phi, that is this. This is rho cosine phi. Y equals rho sine phi, the rho sine phi. As a result, r sine theta equals rho. This is rho cosine phi. Rho sine phi. This is very important. X component is r sine theta cosine phi. R sine y component is r sine theta sine phi. And z component is r cosine theta. The differential area vector for a patch on the surface is parallel to the normal vector. The radial vector is a unit vector along the r equals x, I, y, j, z, k, right? So if we if we divide this one by radius, then this is the unit vector along the radial direction. Because r are common, the unit radial vector is expressed in terms of polar coordinates of polar angle theta and azimuthal angle phi like this. Therefore, the electric field on the surface of the sphere, is 1/4 pi epsilon 0 q over r squared and unit radial vector r hat, and r hat is expressed like this. Finally, the electric flux is computed as a scalar product of electric field that we just have expressed. Electric field on the surface, just substitute this one in here, then we know the area dA is normal to the surface, normal to the sphere, so it should be proportional to the radial vector. So dA vector should be dA times the radial unit vector. So this unit vector and this unit vector, the scalar product of unit vector, unit radial vector is 1. Therefore, the flux element is simplified as. Now, we integrate over the closed surface as that is a sphere, so shell. Then you know the radius r, the surface area of a sphere of radius r is 4 pi r squared. Therefore, if we substitute this one in here, we know the radius r is fixed. This radius r is fixed. Substitute this one in here, r squared cancels. As a result, 1 over 4 pi epsilon 0 r squared q multiplied by 4 pi r squared. We know this r squared cancel. 4 pi cancel. The result is q over epsilon 0. Therefore, a point charge radiates electric field in the radial direction, and if we choose the spherical surface of radius r, then the total electric flux passing through the sphere of radius r is charge q over epsilon 0. This is a very simple expression. This is the crucial point of the Gauss law. Now, we say the Gaussian surface is a closed surface surrounding a charge in a volume V. We have a charge Q. This point charge Q emits electric field. This electric field is a radial direction. We have a spherical symmetry, so it's better to choose a sphere whose center is at the origin where the charge is placed. So this kind of closed spherical closed surface is called Gaussian surface. It does not have to be the spherical, but it depends on the symmetry of the charge distribution. for a point charge, this Gaussian surface it is good to use the Gaussian surface as the closed surface made of sphere. Now, the Gauss law relates the electric field on a Gaussian surface S to the net charge in V enclosed by the surface. As we have seen already, flux equals charge over epsilon zero, where charge Q is enclosed by the closed surface S. d phi, this d phi is the differential electric flux passing the differential area vector dA on a Gaussian surface. If E emits from V, then d phi is positive. dA is toward outside, heading outside. And if the electric field emits, then they are parallel, so d phi is a positive. If dA is in this way and electric field enters into the closed surface, then d phi is negative. For a point charge, a convenient Gaussian surface is a sphere centered at the charge, right? For a uniform charge on a wire, it is a cylinder whose central axis is along the wire. This is wire, charge Q is distributed over the wire. Then, this kind of Gaussian surface is used. For example, electric field is radiated this way. So, this is Gaussian surface. Gaussian surface. For a uniform charge on a wire, that's what we have done already. Okay, cylindrical Gaussian surface for the line charge distribution. For example, we first considered a simple case. Electric field is there is a uniform electric field in this direction. And we consider Gaussian surface. Gaussian surface, it should be closed surface made of a cylinder. We have a cylinder. There's a two lid, left lid, right lid, a kind of cap, and this cylindrical surface. So we have this A surface small a, surface small b, small c, and cylindrical surface B. This Gaussian surface is somehow these three open surfaces. Electric field is constant. You see A and C, the normal dA direction is in here, the A direction is here, and if we take a small patch, dA is in here, and electric field, and electric field. We find that this part, d phi, must be 0 because they are perpendicular. And here, d phi is a positive because they are parallel. And here, d phi is a negative because they are anti-parallel. So, the net flux phi is the sum of fluxes, phi A for this gone, phi B for this, and phi C. The base A, this lead, left side, this lead. The area, an area vector. Area is, this is a radius capital R, so area is pi r squared. Area vector, this is k direction, k hat direction. And this direction is toward left, so minus k. And electric field is constant, so if we substitute this here, what we find is pi r squared is area, electric field strength, and cosine theta is minus 1. So this one is the contribution of this side. C, that is normal regardless of these values, because the angle, where is, oh, C is this side, C is this side. Everything is the same except that the sign is a positive. Hence, these two values are equal in magnitude but opposite sign. Therefore, sum of A and C is exactly 0. And we assume that this is the length L, the radius is R. Hence, we can compute each part. However, because the angle between E, electric field, and differential area element is 90 degrees, the contribution of B vanishes. Therefore, the net flux passing through the Gaussian surface under the constant electric field is 0. Consider the case the electric field is given by the flux of the electric field through an area on the xy plane. xy plane, normal to the xy plane. So along the k hat xy plane. Therefore, it is easy. So we had better define the direction along we have. In a similar manner, we can compute the electric field flux passing each given surface element. Now let us consider Gauss law. In summary, electric field flux integrated over a closed surface that is called the Gaussian surface is charge enclosed by the surface divided by permittivity, vacuum permittivity, epsilon 0. This is Gauss law. This is Gauss law. And this is the electric field flux. So here the flux is charge enclosed by surface, by closed surface that is called Gaussian surface, divided by permittivity, epsilon 0. A very, very simple formula. A point charge Q is at the center of a cubic Gaussian surface. Okay, we could have chosen a spherical surface like this, but it is still allowed. This Gaussian surface doesn't have to be very simple. It could be very, very complicated. Regardless of the complexity of the closed surface that is Gaussian surface, the answer is always the same. So, in case we use this cubic surface, there are 6 faces, and if we choose the center in here, 1, 2, 3, 4, 5, 6 surfaces have the symmetry. The flux passing through here, these 6 fluxes, the flux phi should be 6 times phi 0. Let me call this is phi 0, phi 0, phi 0. Every phase there is a symmetry. Every flux must be the same. And according to Gauss law, it should be charge Q divided by epsilon 0. Hence, phi 0, that is the flux passing through a single surface, is just Q over 6 epsilon 0. Okay. Charge Q is distributed uniformly throughout a spherical insulating shell. We have a shell, spherical shell, and charge Q is uniform charge distribution. The net electric flux through the outer surface of the shell. So outer surface of the shell. So this is a Gaussian surface. So S enclosed is Q. Therefore, phi, according to Gauss law, charge Q is enclosed by the closed surface S. And this is the answer. B. The net electric field flux through the outer surface of the shell is independent of the distribution of the charge. For example, it's possible to have 2q in here and left side minus q. But net charge minus q plus 2q is plus q. This distribution and this distribution, regardless of the distribution, the Gauss law, the right side of the Gauss law does not care about the distribution, but it does care about the sum, the net charge enclosed by the Gaussian surface. 5. The outer surface of the paper towel rolls does not construct the Gaussian surface because it is not closed. Paper towel roll, it is like that. This surface, open surface. So it is not closed. Gaussian surface, Gaussian surface must be closed. Charged isolated conductor. Conductor. Isolated means there is no source of external charge. So there is no source or sink, isolation. And conductor, if there is a electric field, the charge inside the conductor can be redistributed to make the electric field inside vanishing. Let's see. Gauss law permits us to prove an important theorem about conductors. An excess charge in an isolated conductor is always located entirely on the outer surface. The reason is that charge Q is inside, it is unstable. As long as the electric field exists, it moves because QE, F equals QE. If there is an electric field, then the charge moves. If there is a charge inside, then the electric field exists. Therefore, it is impossible to have excess charge inside the conductor. So all of the charge, net excess charge must be distributed on the surface. On the surface only for conductor. So excess charge in an isolated conductor is always located entirely on the outer surface. None of the excess charge is inside the exterior surface. There's the exterior surface outside the exterior surface and inside the exterior surface. Inside the exterior surface, no charge. The electric field E just outside of the isolated conductor is normal to the surface, and its magnitude is, this is very, very important. The reason is that a surface charge density sigma, then electric field on the right is the sigma over 2 epsilon 0, and in here sigma over 2 epsilon 0. This is the usual case for the uniform charge infinite. However, if there is a conductor, the surface is closed, the inside electric field must vanish. Gauss law states that if in is a sigma, out, inside the electric field must vanish. The electric field flux must be Q enclosed over epsilon 0. Therefore, this right side it's outside is sigma over epsilon 0, and this is 0. The sum is a sigma over epsilon 0. So this is the consequence of the Gauss law. Number 2, consider a lump of copper conductor with a charge Q hanging from an insulating thread. So this is isolated conductor. A Gaussian surface S is placed within the matter just inside the actual surface. Okay, we know there's no charge. Inside. The charge, if it is a Q is a positive, it's just on the surface. Because your surface, this Gaussian surface within the matter, just inside. So charge Q is outside of the Gaussian surface. There is no net charge inside this closed surface S, right? No charge. E equals 0 everywhere on S and inside S. The reason is that there is no charge inside. The only charge is on the exact surface, copper surface, and the Gaussian surface does not enclose any net charge. C. The electric flux integrated over the surface S is 0. Therefore, inside the conductor, the electric field vanishes. According to Gauss law, the net charge enclosed by S is 0. Correct. An isolated conductor with a cavity. This empty space is called cavity. Consider a lump of copper with the charge Q hanging from an insulating thread that contains a cavity. The same situation, except that there's an empty space that's called the cavity. The Gaussian surface S lies within the matter, close to the cavity surface. Again, the E equals 0 everywhere on S. The charge is always on the surface, the matter surface, the conductor surface, and the electric field flux integrate to the surface is 0. The situation is exactly the same. All of the charge will be distributed all outside of the surface. Now we shall find a clear derivation of this result. We remember this open space, a plate, metal plate charged with charge distribution sigma emits electric field left and right equally, sigma over 2 epsilon 0 and sigma over 2 epsilon 0. We computed in the last class by integrating the annular region to consider the disk charge distribution, uniform charge distribution over disk, sigma equals q over pi r squared, and we take the limit r goes to infinity, then we have obtained the electric field near the surface, uniformly charged surface is a sigma over 2 epsilon 0. Here we compute the electric field just outside the surface of a conductor by making use of Gauss Law. We consider a small section of surface that is flat enough, a tiny cylindrical spherical surface, a cylindrical Gaussian surface S partially embedded in the section. This is a conductor, and we have chosen Gaussian surface like that. This is the cross-sectional form. So we have B, A, and C. If you rotate this, no. Conductor is there, and Gaussian surface is like that. Okay? A tiny cylindrical Gaussian surface S partially embedded in the surface, and n hat is the unit normal vector heading outside the surface. N hat is unit normal vector heading outside the surface. The electric field, electric field inside the conductor is always vanishing. And electric field on the surface outside is always normal. But in case sigma equals is a positive, electric field emits outside. So inside electric field is 0, outside is constant and parallel to the normal direction. We cut the Gaussian surface into 3 pieces, C, A, B, C, And electric field is in here. The only flux, non-vanishing flux, comes from the surface A. First of all, C, electric field is vanishing. Part of B, electric field is vanishing. Regardless of the fact, electric field outside is normal to this direction, but the surface B is perpendicular to the electric field. Therefore, the only non-vanishing contribution to the electric flux is over the surface A. That is, surface A, EA, where A is the cross-sectional area of this surface. And we apply the Gauss law. Gauss law states that the electric field flux is sum of ABC, and this value is E times area. And Gauss law states that the right side is the charge enclosed over epsilon 0. And charge is uniform. So sigma times A. This one is the charge enclosed by the surface. Sigma is the charge per unit area distributed over the surface. Therefore, sigma A over epsilon 0 equals E times A. A cancels. So electric field is a sigma over epsilon 0. Conductor. Inside the conductor, electric field is 0. Outside the conductor, sigma over epsilon 0. It is different for the plate, open plate. This side, sigma over 2 epsilon 0 to the right, sigma over 2 epsilon 0 to the left if sigma is positive. So there's a striking difference. Very similar, but there is a striking difference between the conducting volume. Conductor inside the conductor, electric field must vanish. And 5. A hollow conductor is positively charged with Q. A small uncharged metal ball is lowered by a because it is a very similar problem. Let me pass this. All right. Why don't we consider number 8? A positive charge Q is placed near a neutral conducting sheet. Neutral conducting sheet. The net charge is 0. A surface A faces Q, charge Q. Surface A is facing Q, and surface B is on the opposite side. So, actually this sheet, if we magnify this sheet, this A side and B side is over there. Inside the conductor, electric field is vanishing. Anyway, we have charge Q and minus Q. Negative charge is distributed over there, and positive charge is distributed over there to make the net charge is vanish. So A is negatively charged, B is positively charged. Inside the conductor, the field is always 0. Cylindrical symmetry. If we consider wire charged with uniform charge density, we can make use of a cylindrical coordinate system. Cylindrical coordinate system is used the azimuthal angle we introduced when we consider the spherical coordinate system. Just the x, y coordinates are. So this rho is the radius, planar radius on the xy plane. So radial direction is this, and tangential direction is written in the form phi. You find that rho hat dot rho equals 1, phi hat dot phi equals 1, rho hat dot phi, they are orthogonal. Sure, rho phi must be k. So this is like I, j, k. I cross j equal k, j cross k, I, k cross I, j. So something like that. We have rho phi k. These three make a cyclic triad. Because if there is a charge distribution, uniform charge distribution over a straight wire, we can take the Gaussian surface and electric field. Suppose that we have positively charged wire, that electric field must be the radial direction. This radial direction along the rho hat. And this is a rho. Rho and H. Here for area of the surface, we have 3 parts, this part and this part. Because the electric field is along the radial direction and surface on top and bottom perpendicular to the electric field, we don't care about these 2 surfaces. The only non-vanishing contribution comes from the surface. This surface. Okay? Electric field is outside, toward the outside. And electric field is constant at a fixed rho. So using this, we have the area of this surface. This is H, 2 pi rho. And electric field is uniform. Electric field is uniform. Area is 2 pi rho H. 2 pi rho H. So electric field flux is obtained like that. And we have charge. What is the charge? That is line charge density Q over H. So that's charge enclosed equals lambda times H. Therefore, the left-hand side, this one is in here, and right-hand side, Gauss Law states that lambda H is the charge enclosed by the Gaussian surface. Finally, the magnitude of the electric field is obtained like that, 2 pi rho, 2 pi rho. Epsilon 0 is in here, permittivity constant, and the radial direction rho. Finally, electric field due to a uniform line charge is obtained by making use of the Gauss law very easily. This is a cylindrical symmetry, and previously we used spherical symmetry to find out spherical symmetry. For the line charge, we use cylindrical symmetry, and we have planar symmetry. We redo the calculation for this electric field near the surface of uniformly charged plate with sigma q over a. And in open space, we have charged plate. An electric field, if it is a positively charged plate, electric field emits to the right and to the left, and there is a left-right symmetry. And this E plus and E minus, their magnitude must be the same, but direction will be opposite. We do the same calculation by making use of the previous calculation. Okay. We have Gaussian surface like this. This is a C, this is A, and B. We know the electric field inside the conductor is vanishing. Outside the conductor, it is normal to the plane, but in the surface vector is always normal to the electric field. Therefore, this part, we don't have to consider this part, and we only consider this part and this part. Right side, and left side. Right side and left side. Alright? And right side is A, left side is C. Right side A, left side is C. And area is the same. Area is the same. Strength of the electric field must be the same. And we know the electric field on the right is to the right, and surface is to the right. They are parallel. Electric field on the left, to the left, and surface is to the left. So they are parallel. So this right side, left side, they are equal. There are two contributions, EA, EA. So 2 times EA. And contribution from surface B must vanish. So surface B contribution does not exist. And Q enclosed by the Gaussian surfaces, sigma times area. So sigma times area over epsilon 0. Sigma times A epsilon 0 equals 2EA. Therefore, AA cancels and E equals sigma over 2 epsilon 0. Therefore, on the right side is proportional to K, and on the left side it is proportional to minus K. So this, if sigma is positive. If sigma is a negative, electric field is opposite direction. Next, we consider the case. We have sigma Then electric field is sigma over 2 epsilon 0, sigma over 2 epsilon 0. If it is minus sigma, then the same amount, sigma over 2 epsilon 0, sigma over 2 epsilon 0. Therefore, the contribution on the left, this one is written in blue. Contribution of this right side is hence the resultant contribution that survives is between the two plates. So we have electric field inside sigma over epsilon 0 and 0, 0. In case we have this plus distribution, emits, emits, emits. Inside the plate vanishes, but outside they survive. So sigma over epsilon 0, sigma over epsilon 0, 0. And direction is this, right? That's shown here. Spherical symmetry. If we have spherical symmetry, then we use a spherical surface for the Gaussian surface. Next, we have some problem. You can download the following paper by clicking the hypertext given here. Okay. This paper considered derivation of Jacobian formula with Dirac delta function, but you don't have to worry about not knowing the Dirac delta function. Then I want to talk about the Jacobian. Jacobian is just like we can see in equation 1. We consider the surface. We compute the surface. This is a kind of surface area of a disk evaluated by making use of XY coordinate system. But it is usually easier to compute this if you use polar coordinates. And we remember ds area, the area is 2 pi r dr, something like that. But we can compute this area in a rather complicated way, slicing this the dx and the height multiply this one. So this area calculation must be the same. So this is a Cartesian coordinate Cartesian, and this is a polar coordinate. Any calculation must be the same. But when we do these calculations, you have some additional factor that did not appear in computing the area by making use of the Cartesian coordinates. This is called, the additional factor is called the Jacobian. And Jacobian is very important in multivariable calculation. So I hope you study a little bit about Jacobian by making use of this relation. Read through this paper, specifically useful part for your convenience. So that's it for today. Thank you.